Hello, this is video 32. In this video, we're going to start our discussion of circular motion with centripetal acceleration. So I like to start this out with a question. A car drives with constant speed around a curve. Is there a net force on the car as it rounds the curve? So your instinct might be that you see, oh, constant speed. She said constant speed, equilibrium, no net force. But it has to be constant velocity, not constant speed. So the answer is that there is actually a net force, because even though you have a constant speed, you're rounding the curve. That means you're changing direction. When you're changing direction, that's an acceleration, and that means that's a force. That acceleration is called a centripetal acceleration. So whenever you're moving in a circle, if you're moving at constant speed, it's called uniform circular motion. And that acceleration exists because you're changing directions all the time. That means that your velocity is changing. This picture shows here. And then the direction of this acceleration is actually toward the center of the circle. And you could actually see this if you did some vector subtraction with the velocities, but I'll skip that step. And the magnitude of the acceleration is v squared over r. Also, I'm going to skip the derivation, but I did make a note about this equation. What we can see from this equation, which is in line with what we know, is that centripetal acceleration is greater at high speeds and in sharp curves. You feel more acceleration when you're turning that turn faster and then when it's a sharper curve. And you can see on the top is the speed, so as you increase the speed, it increases your acceleration. And then the radius of the circle is on the denominator. So as you decrease the radius, or as you make that turn more sharp, that's when the acceleration goes up. So the equation makes sense. Even though we don't derive it, we can just accept it. A toy car moves around a circular track at constant speed. It suddenly doubles its speed, a change of a factor of 2. As a result, the centripetal acceleration changes by what factor? So I like these types of questions because they don't require you to use your calculator. But the first thing is you have to know which equation this is related to. This is related to centripetal acceleration, so v squared over r. And then it requires you to simply look at the equation and see, okay, what happens if you double the speed? So what you can do is you see, okay, well, I'm going to put 2v, but don't just put 2v in because it's 2v squared. Make sure you square it. And then you see that you get 4v squared over r. So when you double the speed, you now actually have 4 times the acceleration that you had before. And let's finish this video with a quick example, just using the equation for centripetal acceleration. World-class female short track speed skaters can cover the 500 meters of a race in 45 seconds. The most challenging elements of the race are the turns, which are very tight, with a radius of approximately 11 meters. Estimate the magnitude of the skater's centripetal acceleration in a turn. So centripetal acceleration is v squared over r. So we need to know the speed. We're not given the speed, but we can estimate because we have a distance, 500 meters, over 45 seconds is the time. So I'm using the average speed equation is distance over time. When we do this, this gives us a speed of about 11 meters per second. And now we need to find the centripetal acceleration. So plug in this speed in the equation, v squared, 11 squared, and the radius was also 11. So that means that the centripetal acceleration is approximately 11 meters per second squared. So this is indeed a high acceleration. It's higher than g, which is 9.8. But in order to be able to do this, they do have to definitely lean into that circle. So this was centripetal acceleration. Remember, even if you're moving at constant speed, if you're going around a circle, you definitely have some acceleration, which in turn means that you have a force. And this is going to be the topic of the next video.